Our next topic is molecular orbital theory, our second of two. Molecular orbital theory turns out to be particularly good at predicting the properties of different molecules and can be applied more widely, whereas valence bond theory is more useful for organic molecules like we looked at before. When we think about molecular orbital theory, we start from the idea that electrons do have to be described by wave functions. In atoms, that would be our 1s, 2s, 2p. And remember, we normally focus on the fact that the wave function squared is probability, but the wave function alone gives rise to those wave-like properties of matter. So the electron can interfere constructively or destructively. So here we think about like a wave on a pond. Here we put two stones maybe and drop them right here in our pond. The two ripple patterns create these regions of constructive and destructive interference. The same thing can happen with electrons, and we'll see that in a second. So how this relates to our bonding theory is, we've looked at these before. Molecules assume the lowest energy, shape, bond length, electron distribution, and so forth by forming the strongest possible bonds and minimizing those electron-electron repulsions. To form a strong bond, we're going to maximize the orbital overlap. So head-on is going to be better than side-on. Sigma bonds typically are stronger than pi bonds. And we're also going to maximize the energy match. So it turns out that the closer in energy the two orbitals are, the stronger the interaction between the orbitals. If orbitals are very far apart in energy, they can't actually interact. So to motivate why we need this new theory, let's look at the case of molecular oxygen versus molecular nitrogen. Nitrogen, when you put it through a magnetic field here, it pours right through in this strong magnetic field because it's weakly repelled by it. Oxygen is strongly attracted. That only happens for paramagnetic compounds. But if we look at valence bond theory, we would predict we have this OO double bond where we have one sigma and one pi bond, and then two lone pairs on each oxygen. That would show that all the electrons would be paired and predict that O2 is diamagnetic, which completely disagrees with experiment where we find oxygen having these unpaired electrons and strongly attracted to a magnetic field. One of the ways people are able to develop oxygen sensors in World War II and early submarines because oxygen is the only paramagnetic compound in air. So I think it's useful to just start by doing an example for MO theory. So when we think about a molecular orbital diagram, we're going to start by thinking about our orbitals, and then at the end we'll only fill it with electrons, just like when we did atomic electron configurations. Each atom is going to contribute its valence atomic orbitals to the picture. So let's use H2 as an example. For H2, we have two hydrogen atoms here, so I'll put those on the left and the right. On the y-axis, I have the energy, so this is showing low energy orbitals down here, high energy orbitals up here. Now let's apply rule number 2. Each atom contributes its valence atomics orbitals, while hydrogen, that's electron configuration, is 1s1. So its valence atomic orbital is just the n equals 1 shell. So that's just the 1s orbital. Each hydrogen has a 1s orbital. Next, we'll mix the atomic orbitals to form molecular orbitals. So when two orbitals mix, one is going to become lower in energy, that's a bonding orbital, and one becomes higher in energy, an anti-bonding orbital. Let's see what that looks like for H2. So for H2, we're going to mix the 1s orbital on each atom. When we do that, one orbital, so our MOs are going to be in the middle of this diagram here. And let's show what happens to the first one here. So this orbital down here I get by taking the 1s orbital on each atom and adding it together. So this hydrogen, say, is the hydrogen on the left, and this hydrogen is the hydrogen on the right. When I mix them together, I have these two orbitals coming together, and I'm adding those two things. Those things are both positive, so the overall orbital I get looks something like this. The electrons are building up in this region between the two atoms, interfering constructively, and that will be my bonding orbital. It's more stable, it's piling up electrons between the two atoms. The other orbital I get is going to come up here. Now this orbital I'm going to get by taking one orbital positive, but the other orbitals I'm going to have negative, and I'll represent that by shading it in. When I do that, I'm adding a positive number with a negative number, so in between the two atoms, the electron density is going to actually go away. I'm going to get destructive interference. And so what my resulting orbital will look like is something like this, where the electron actually has zero probability of being located exactly halfway between the two atoms. This is our antibonding orbital. This is, a very unfavorable way for the electron to be because it's it wants to be shared between the two atoms in the middle. This is unfavorable where the electron has to be forced to the edges of the molecule. Next, let's think about where I drew those two lines. So I drew one orbital down here by a certain amount, one orbital up here by a certain amount. And this comes into our sort of bonding principles. So in this case, these orbitals overlap very well. Those hydrogen 1s orbitals have a nice head-to-head overlap. That's a sigma bond. Very good overlap, and they have a perfect energy match. Those are those other two factors. So because it has strong overlap and a good energy match, we get a very strong interaction between these two orbitals. What that's going to do is give us a very low energy bonding orbital and a very high energy antibonding orbital. There's sort of no free lunch. The lower in energy that your bonding orbital gets, the higher in energy that your antibonding orbital gets. They sort of spread apart equal and opposite amounts when we interact two orbitals. Next, we'll label the orbitals that we've created. So we'll label them first by the symmetry of how the bonding looks, whether it's sigma or pi. Then the source orbital will be our subscript. So in this case, we have a sigma bond. So this is going to be the sigma orbital. Next, the subscript here is what orbitals I used to make it. So that's the 1s orbital I used. And up here, I'm going to get sigma 1s as well. But this one will have the star because that's the antibonding orbital. So I always use star to represent an antibonding orbital that got higher in energy. Next, I'm ready to fill this structure with valence electrons. So in this case, for H2, each hydrogen brought one valence electron. So I have two valence electrons, and then the way those go in are just the same way they would in an atomic orbital configuration. We fill the orbitals from low to high and put one electron in each orbital spin up before pairing them as necessary. Now, note these 1s orbitals on the sides are sort of gone. The place I'm going to fill the electrons is only in these center molecular orbitals. The atomic orbitals that I used are now gone. And the only orbitals I have are the molecular orbitals. So I have two electrons. They'll go in the sigma 1s orbital. And that's the molecular orbital diagram for H2. Now that I have the MO diagram, I can do a couple of different things with it. So one thing I can calculate is what's called the bond order. This I get by taking half of the bonding electrons minus the antibonding electrons. So bonding electrons, how many electrons are in bonding orbitals? Well, in this case, that's these sigma 1s electrons. So there's two electrons there. And now antibonding electrons, well, there's an antibonding orbital, but there's no electrons in it. So it just ends up being 1/2 of 2 minus 0, which is 1 is the bond order here. The other thing I can do is determine the magnetic properties. So that is the same way we did before. In this case, there's 0 unpaired electrons. So I can also say that H2 should be diamagnetic because there are no unpaired electrons. Okay, these slides just give some pictures to what we drew out by hand there. When we mix to form bonding and antibonding orbitals, the bonding orbital looks like this, building up electrons between the two atoms. Antibonding takes electrons away from the region between the two atoms. And again, the bonding orbital is lower in energy, antibonding orbital is higher in energy, and we use the normal rules for filling these. So from low to high, and one electron spin up before pairing them. Again, the labels, those same rules, as shown here. Okay, the molecular orbital diagrams that we're going to look at in this class are first and second period elements, the homonuclear diatomics, things like H2C2F2, as well as heteronuclear diatomics. Let's do one more simple example before moving on to the more complicated ones. So for He₂, let's do the molecular orbital diagram, the bond order, and magnetic properties. So first, remember, we're going to worry about the electrons. So we'll draw out our energy axis here, energy. We have two helium atoms coming in. And if we think about its valence orbital, each helium has an electron configuration of 1s2, so its valence electrons are in n equals 1. So we start with a 1s orbital on each of those. And then they mix just the same way they did for hydrogen. So this is one of the advantages of MO theory is that anytime I have two 1s orbitals mixing, I'm going to get this same MO diagram, where I have a sigma 1s bonding orbital and a sigma 1s star antibonding orbital. Now, though, the only thing that's different is the number of electrons. So for He2, each brought 2 valence electrons, so I have 4 valence electrons to fill. So that's, again, fill from low to high. 1s, the sigma 1s gets 2 electrons, and I have 2 more. They go up here. So this is sort of my final MO diagram for He2. We can calculate the bond order, 1/2 bonding minus antibonding. In this case, that's 2 electrons in bonding orbitals down here. The antibonding orbitals always have that star on them, so 2 electrons in antibonding orbitals. And we get 1/2 of 2 minus 2 is just equal to 0 for the bond order. What a bond order of 0 means is that there's no bond between these two atoms. So helium is a noble gas. It doesn't actually form the helium-2 molecule. And that's what this bond order of 0 means. There's nothing holding helium together. And it actually will just sit as neutral atoms on its own, rather than forming this molecule. If it did exist, it would be diamagnetic as well, because there's 2 electrons here, 2 electrons there. This shows the 2 cases here. The one new thing we want to look at here is this idea of the MO electron configuration. So if we don't want to draw out this whole diagram, we can answer all of our questions by just writing out the electron configuration here, where we put the orbital here. We have to put it in parentheses because we might have the superscript star here for antibonding orbitals. So we put each orbital in parentheses, and then as a superscript around the parentheses, we put the number of electrons in each of those molecular orbitals. So sigma 1s2 is a representation of the H2 molecule. For He2, 2 electrons in that sigma 1s orbital, just as before, and now there's 2 electrons in the sigma 1s star orbital, so there's a sigma 1s star 2 as well. And you can see just the same way that when you think about electron configurations, rather than drawing out the diagram with the energies of each orbital and the number of electrons, we can use that shorthand notation where we put, say for fluorine, right, we would just write 1s2, 2s2, 2p5 for its electron configuration. That gives us the same information as we would by drawing out the energy axis with the relative energies of each orbital. Okay, one of the powerful things that molecular orbital theory does is give us this idea of bond order. And what we know from also from valence bond theory is the bond order sort of tells us, is this a single bond, double bond, triple bond, or somewhere in the middle? The larger the bond order, the stronger the chemical bond. So triple bond would be stronger than a single bond, say. Next, the larger the bond order, the shorter the chemical bond. Here's some evidence from the hydrocarbons. This is C2H6 with a single bond connecting the atoms. That's a relatively long bond, and it takes relatively little energy to break this bond. A double bond would take more energy you'd have to put in to break it, so it's a stronger bond, and these atoms are closer together as well, down 20 picometers shorter. So a triple bond is shorter still. So the larger the bond order, the stronger the bond. The larger the bond order, the shorter the bond, which is going to be important for predicting properties from the molecular orbital diagram. Now let's do our more complicated example. So let's look at O2 and apply our rules to get the molecular orbital diagram for 2, and then its bond order and magnetic properties. Okay, so we have to worry about the orbitals first. We'll draw out our energy axis here. So we've got an oxygen atom on each side here. Now, first we need to figure out its valence orbitals. So oxygen, if we remember from its electron configuration, oxygen is 1s2, 2s2, 2p4. Those are the 8 electrons, and so it has 2s and 2p valence orbitals. So those are the ones we need to put into the diagram. Which one is lower in energy? Well, we fill the s first, so that's the one that was lower in energy. So if we look at each oxygen atom, it has 2s, which is just a single orbital. Then the 2p, remember the 2p subshell can hold 6 electrons. There's 3 2p orbitals. So we need to put 3 lines in our diagram for the 2p subshell. And since it's oxygen on each side, that's the same on both sides here. So this is our diagram for O2. We start now, remember n orbitals in, n orbitals out. So here we have 8 total orbitals that we're starting with, 4 from each. So we're going to get 8 molecular orbitals out when we mix these together. The first thing we can do is mix the 2s. That looks the exact same as sort of the 1s looked. So let's put those in here first. So this is going to be a sigma 2s and a sigma 2s star. Bonding, lower in energy, anti-bonding, higher in energy. It looks the exact same as the 1s, basically. The bonding orbital is going to pile up the electrons between the 2 atoms and look something like this. The anti-bonding orbital is going to pull electrons away from the 2 atoms and look something like that. Next, let's go to the 2p orbitals. So for the 2p orbitals, there's 3 2p orbitals. We'll call this the 2p x. I'll call that the 2py. The 2px is this one coming out of the board there. So 2px, we'll call that one. And then the other one is the 2pz, which is pointed right at the other atom. So this is the 2pz orbitals here connecting, right on the line connecting the 2 atoms. Remember that the 2p orbital has a positive and a negative lobe. So when I think about drawing it, I might draw each one as something like this. And here's both of them for this one. This is the 2pz. So 3 2p orbitals, so we're going to get 3 sets of bonding and anti-bonding orbitals. Let's look at this 2pz combination first. So here, if we look at the 2pz's, these, if we try to identify what type of bond we formed, we're colliding head-on here. So this is a sigma bond. So I'll put that in there first. I'm going to label it then as the sigma 2p. I'm not going to call it 2pz just for the sake of usefulness. So this is going to look something like this. Sigma 2pz, and then again we always get an equal and opposite antibonding orbitals. So I've got to put the antibonding orbital up there. Sigma 2pz star. Now I have these 2px and y's to combine. So let's look at the y because that's easier to draw. So that's this combination like this. So we've added these up together. Now we can see there's no electrons between the 2 atoms. This is an overlap above and below the plane. So this is going to be a pi bond. And it's actually going to be the same for this orbital. That one's harder to draw, but I'll try, right? That's coming into and out of the board, so it's going to look something like this. That's also a pi bond there as well. So these are going to be pi 2p orbitals. Now the question is, where do those fall in our diagram relative to this one? Well, here we can apply this rule. The better the overlap, the stronger the interaction. So since the 2pz orbital has better interaction, it's the sigma bond, that's going to give us a stronger interaction. The pi bond is going to be a weaker bond and a weaker interaction. So we have pi 2p here, and up here pi star 2p. And that is our final diagram. So we have these 8 orbitals, sigma 2s, 2s star, pi 2p, sigma 2p, pi 2p, 2 of those orbitals, and then 2 pi star, 2 sigma stars. We always have equal number of bonding and antibonding orbitals, so we have 1, 2, 3, 4 bonding orbitals and 1, 2, 3, 4 antibonding orbitals. Now we're ready to fill this diagram with electrons. So each oxygen brought 6 valence electrons. So O2 has 12 electrons. We'll fill those from low to high and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Thinking about the magnetic properties, we have these 2 unpaired electrons. That's the huge difference with valence bond theory. We have these 2 unpaired electrons, which makes this paramagnetic, which matches experiment. The bond order, we can show that calculation as well here. Adding that up, we have a total of 2, 4, 6, 8 electrons in bonding orbitals, minus 2, 4 electrons in antibonding orbitals. And that gives us a bond order of 1/2 of 4 is equal to 2, which does match experiment as well. Now, most of the time we're not going to have to go through all the work of drawing this diagram, but it's not completely unreasonable to do. It goes right in line with our sort of bonding principles from back here. But again, what's so powerful is now that we've drawn this diagram once, we really don't need to draw it again. We can basically just remember the order of the orbitals and either draw these orbitals out and fill them with electrons, or do that sort of compact MO electron configuration where we just write this out in that line format. In this case, something like this: sigma 2s 2, sigma 2s star 2, sigma 2p2, pi 2p4, and sigma star 2p2. Here's that same information, just showing the pictures maybe a little bit clearer of all the different pi combinations we get: bonding, anti-bonding for pi, and bonding and anti-bonding for sigma. So here's all of the different orders of the second period energies and elements. So O2 and F2 look just like we showed, where the sigma 2p comes below the pi 2p. Now, it turns out that those orbitals are actually flipped for the other second period diatomics. That's basically because of how these orbitals end up close in energy and continue to mix to form the lowest energy possible bonding and highest energy possible anti-bonding orbitals. Not a huge point of concern for us, but it's important for doing your diagrams. So the thing you're going to need to really remember from molecular orbital theory is this picture. So this is how we're going to fill out our diagrams without having to do it from scratch each time. The sigma 2s orbitals always come lowest because the 2s atomic orbitals are lower energy than the 2p. So you have sigma 2s star. Then for the pi's, again, there's 3 2p orbitals. So there's going to be 3 bonding, 3 anti-bonding orbitals. As we showed before, 2 of those are pi orbitals. 1 is another sigma orbital. In general, the pi 2p orbital is going to come first. Now, again, it sort of doesn't match the logic, but it does turn out that is the actual experimental order. Again, what happens is that all of these sigma 2s and sigma 2s star orbitals get pushed down in energy, and all these up here get pushed down in energy to form the best bonds and basically the highest energy anti-bonding orbitals we can. And that's just sort of something you'll have to remember, is that this is the normal order with the pi 2p below the sigma 2p, but these are flipped for only these 3, O2, F2, and Ne2. So anything else, we'll look at things like OF or NO. Any of these are going to have this normal diagram. So it's only O2, F2, and Ne2 where we'll have to flip these orbitals back to the way we drew it out at first. And so that's what you need to remember. If you like, you can remember it based on the periodic table. The cutoff, it comes between N and O. Below these are P for pi lower and S for sigma lower. So as soon as you get to oxygen, the sigma orbital is lower, S for sigma. For nitrogen and anything to the left of that, the pi is lower. So that could be a useful mnemonic for you. Okay, so here's our first exercise using the MO diagram on the previous slide. Write the MO electron configuration, determine the bond order for each of the following, and label them as paramagnetic and diamagnetic. Okay, so here's the solution. Let's start with Li2. So here we can see Li2, that's the normal diagram, so I'll just sort of draw out that normal diagram. Okay, so again, remember the 2s part is first, 2s star, and now the pi 2p is lower than the sigma 2p in the 2p part of the diagram. So for Li2, that's pretty simple. There's just 1 valence electron in each lithium. So Li2 just has these 2 valence electrons, and that will look like sigma 2s2 in the MO electron config. Carbon, each carbon brought 4 valence electrons, so 4 times 2 is equal to 8 valence electrons. So we have the 2. And now for carbon, we'll put in 6 more. 3, 4, 5, 6, 7, 8. So carbon will be sigma 2s2, sigma 2s star 2, and pi 2p4. Just filling those in from low to high. Now F2, remember, that's one of our exceptions where we have to flip the order of the orbitals. So let's do that. Now that we have those orbitals flipped, we count our valence electrons. Each fluorine brought 7, so we have 14, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's our F2 electron configuration with 14 electrons. Sigma 2p is lower, so it comes first in our electron configuration. Now Ne2 has 8 electrons each, so 8 times 2 is 16 valence electrons. We just need 2 more valence electrons, which go in that sigma star 2p. So that's the electron configuration of Ne2. Next, the bond orders. So 1/2 bonding minus antibonding. We can sort of do that without really writing it down for most of these cases, just sort of in your head. Li2 has 2 bonding electrons, so 1/2 of 2 is just a bond order of 1. Next, for C2, that has 6 bonding electrons and 2 antibonding electrons, so that's going to be 1/2 of 6 minus 2, which is 2. F2 has a bunch of electrons. 2, 4, 8 are bonding electrons, and 6 are going to be antibonding electrons if I count those up. So that's going to be 1/2 8 minus 6, which is just equal to 1. Ne2, on the other hand, is I have 2 extra antibonding electrons here, so 2, 6, 8 total antibonding electrons, so 1/2 8 minus 8 is equal to 0 as the bond order there. For the magnetic properties, the part B, well, again, we sort of need to go back from this picture to figure out whether these orbitals are filled or not. So that last orbital, we always have to check if it's filled. Li2, yes, that orbital was filled with 2 electrons in it. So that is 0 unpaired electrons, which makes it diamagnetic. C2 has a pi 2p4. 4 electrons in that pi 2p is completely filled. 2 orbitals hold 4 electrons. So that's also 0 unpaired and diamagnetic. F2 similarly, 4 electrons in that pi star 2p, which makes it completely filled, so 0 unpaired. Dia as well, and Ne2 is the one that we have up here. We can see that one has all filled orbitals as well, and is also diamagnetic. Here's a few of the other second period diatomics showing their electron configurations. Note this table of data showing what we expect to see experimentally and how it correlates with the bond order. And number of unpaired electrons, pair or diamagnetic. So let's look here. Be2 has a bond order of 0 because it's 2 bonding and 2 antibonding electrons, and we do see that that is in fact unstable. Next, going from like B2 to C2, B2 has a bond order of 1, C2 has a bond order of 2, and we can see the bond energy goes up quite a bit there. It just about doubles, consistent with C2 having a stronger bond, higher bond order. N2, a stronger bond still, going from a bond order of 2 to a bond order of 3, even larger bond energy. As we go back down, the bond energy starts to decrease along with the bond order. Now, one of the really great things about molecular orbital theory is that ions work the exact same way, and we don't have anything really new to do. All we have to do is use the same diagram and add electrons for anions, remove electrons for cations. So for He2+, the only thing that's different about that is when we count the electrons, because it has that one positive charge, it's 2 by 2 is equal to 4 electrons for He, but I have to remove that 1 electron for the +1 charge, so it's just 3 electrons. And so the picture looks like this. Sigma 1s2, and then the third electron goes in the sigma star 1s orbital. So it looks like this. The bond order is 1/2, and He2+ is a relatively unstable, but a ion that you can form and study in lasers and things like that. For our next exercise, write the MO electron configuration and fill out that table for C2+ and C2- ions. Okay, so starting with the MO electron configurations, C2+ would have, instead of 8 electrons, because of that plus charge, it only has 7. So as a result, we have to lose one of these electrons. So the electron configuration for C2+ would just be sigma 2s2, sigma star 2s2, and then just 3 electrons here in the pi 2p orbital. The bond order then, instead of having 4 of these bonding electrons, I just have 3. So as a result, my bond order calculation is just 5 bonding electrons minus 2 antibonding electrons, so only 1.5 for the bond order. That makes sense. I took away a bonding electron. That made the bond weaker. The magnetic properties, we have paramagnetic because of that one unpaired electron. For C2-, that now instead of having 7 electrons, I'm going to have 8 plus 1, so 9 electrons. Compared to C2+, I need to add 2 more electrons, so 1, 2, and that's going to look like this. Now, after I have the electron configuration there, the bonding electrons is 2, 6, 7, so I have 7 bonding electrons, and still just 2 antibonding electrons. I've added, compared to C2+, I've added 2 more bonding electrons, which adds 1 to the bond order. So 1/2 of 5 is 2.5 for the bond order here. And again, we can see there's a single unpaired electron, which makes it paramagnetic. Evaluate the bond energy and bond length. So those are both related to the bond order. A larger bond order is going to be a shorter, stronger bond. And stronger means a larger bond energy. It would also be more stable. So this bond energy here, this is going to also be sort of stability here. A higher bond energy is going to be more stable. It's harder to break a stronger bond than a weaker bond. So here, again, we can see that a larger bond order is a stronger bond. So the strongest bond is C2-, because it has the largest bond order. The weakest bond is C2+, because it has the smallest bond order, and C2 falls right in the middle. Now we can see for bond length, the larger the bond order is, the shorter the bond. So the C2- is going to, it's all going to be flipped. C2- is the shortest bond, C2 is in the middle, and C2+ is the longest bond. That does, in fact, agree with experiment. Okay, I was somewhat wrong there. The C2- is actually slightly longer than C2. Well, we can maybe rationalize that based on that negative charge, meaning the electrons need to spread out a little bit more to accommodate that negative charge. Unfortunate gap with what we expected there, but the rest of it did agree well. Next, let's look at heteronuclear diatomics. So these, what we're going to do in class problem-wise is very similar to homonuclear, but there's very nice connection to concepts like electronegativity, bond polarity that we'll look at here shortly. So for HHE, if we look at that heteronuclear molecule, the hydrogen 1s is higher in energy than the helium 1s. We can think about this in terms of maybe the ionization energy. This electron here in helium is more stable because it has that larger Z effective as we go from hydrogen over to helium, so it's going to be harder to pull this electron away. So it starts lower in energy. What that means then is when we make the molecule right here, the bonding orbital is going to look more like the helium orbital to make the lowest energy possible orbital. I'll just exaggerate this for a second. It's going to spend a lot of time on helium and only a little bit of time on hydrogen. Then, consequently, the antibonding orbital, to make that as high in energy as possible, it's going to spend a lot of time near hydrogen and just a little bit of time near helium. What this looks like then, since the electron is spending most of its time near helium, helium is going to be partially negative and hydrogen is going to be partially positive in this molecule. So we'll make a nice polar covalent bond. And that just falls right out of molecular orbital theory, this sort of continuum between a pure covalent bond and this nice polar covalent bond. So this is just showing that here. The bonding orbital will have more helium character. The antibonding MO will have more hydrogen character. Okay, on the periodic table, if we're doing heteronuclear diatomics here, we're going to always use this diagram right here with the pi 2p lower in energy than the sigma 2p. Other than that, the exact same thing applies though. NO, so oxygen, is more electronegative. It's going to be lower more stable orbitals to start with. Greater Z effective would be the other way to think about it. But other than that, it works exactly the same when we draw out the molecular orbital picture and the bond order and so forth. Okay, here's our next problem looking at heteronuclear molecules. Okay, the MO electron configuration for OF minus, we're going to have 6 plus 7 plus 1 electron for that minus charge, so 14 electrons in the MO configuration. We'll fill those 14 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which gives an MO electron configuration of this right here, as all written out. Now, the contributes more to the bonding orbitals, right? That's going to be the one that has more stable valence orbitals, which we can think about either in terms of electronegativity. More electronegative is going to pull those sort of shared electrons more, or sort of Z effective in this case would also work, right? So fluorine has a bigger Z effective. And if we think about sort of the neutral atoms here, fluorine's orbitals are going to start a little bit lower. The 2s on fluorine is a little bit lower than the 2s on oxygen. Similarly for the 2p. The 2p on fluorine is a little lower than the 2p on oxygen. So since those fluorine orbitals are more stable, the molecular orbitals that are bonding and lower in energy are going to be more like fluorine. So fluorine is more electronegative and will contribute more to the bonding orbitals. Cn minus, if we count that one out, that one just has 4 plus 5 plus 1 is equal to 10 valence electrons. So those 10 valence electrons are just enough to fill 2, 4, 6, 8, 10 right here. Again, to figure out which one contributes more to bonding, that's going to be the more electronegative one. If we look on our periodic table, nitrogen a little bit more to the right, bigger Z effective, so nitrogen's orbitals are a little bit more stable and contribute more to the bonding orbital. NO and NO minus is the next part. So again, oxygen is more electronegative, that will contribute more to the bonding orbitals. NO minus here has 1 extra electron compared to NO, so that will have an electron configuration of sigma 2s2, sigma star 2s2, pi 2p4, sigma 2p2, sigma 2p star 2, as shown here, 1 extra electron in the antibonding orbital. Okay, I've filled in the bond orders there, just using our formula. Bonding, 1/2 bonding minus antibonding electrons, you should get these bond orders. Comparing NO and NO minus, now we can actually, for those two, compare the length since it's the same atoms that are bonded together. So NO minus has a smaller bond order, and that makes it a weaker, longer bond. So, okay, so that's that, NO minus with the longer bond. That does agree with experiment in this case. About 0.1 angstroms longer in this case. Okay, just to show the power of molecular orbital theory, here's an example of LIF. So LIF as a solid, if we thought about it there, well, Li is a metal, F is a nonmetal, so we could say in the solid state, this is going to be an ionic bond, and an LIF solid is ionic, but we can turn LIF into a gas where it exists as LIF molecules. What are the properties of that LIF molecule? Well, we can draw out what the molecular orbitals look like. These are both second period diatomics, but in this case, it's important to note that the orbitals on fluorine are all much lower than the orbitals on lithium. So if we think about the 2s orbital here, this orbital is just so much lower in energy than the 2s on lithium that we're probably not going to get much interaction there. Those orbitals are going to be too far apart to interact. And even the 2p on fluorine compared to the 2s on lithium, the 2p is much, much lower in energy. So we're only going to get a weak interaction. This sigma bonding orbital here, which looks something like this, the 2pz, say, on fluorine interacting with the 2s on lithium, is going to mainly be a fluorine type orbital. So I guess to draw that better, it would really look more like that. It'll spend most of its time on fluorine and just a little bit of time on lithium. So really what this is much more like an ionic bond. What's happening mainly here is that this electron from lithium is getting transferred to fluorine, and that's why we see stabilization in the LiF molecule here. There's a little bit of covalent character there, the fact that we have a little bit of lowering in energy when this 2p mixes with the 2s. But this is sort of a nice continuum example where we can sort of smoothly go between a pure covalent bond and, in this case, a nearly completely ionic bond using the same theory. Another case here just to think about is all those cases in fluid structures where we had to use resonance and we have multiple resonance structures. MO theory does a beautiful job of describing those. So if we think about something like ozone, where we had these two different resonance structures, and we said, well, actually, what happens in practice in the molecule is that we have about a 1.5 bond order here, right? Single bond, double bond. Because of resonance, maybe it's roughly a 1.5 bond order in each case to each of those oxygen atoms. We can actually, in MO theory, draw out a big delocalized molecular orbital that shows there's one pi bond shared across all three atoms. That works out really well and is incredibly important for understanding the reactivity of different molecules. We can also then easily think about the excited states and what happens when ozone goes through different reactions. Just one more time before you get started on problems for this. Here's the key diagram you need to know for molecular orbital theory, with this being the common order and flipping these orbitals for O2, F2, and Ne2.